In the previous video, we looked at how to conduct a goodness of fit test using the multinomial distribution. By now, it is probably obvious to you that the multinomial distribution can be difficult to construct once you get beyond very small sample sizes. Yet, in every research study, we want to be able to make as many observations as we possibly can. That could lead to some difficulties with the multinomial distribution, so we need a large sample goodness of fit test, and that is the subject of this video. I begin with an example. A virus persists in 3 variants, A, B, and C. 1 year ago, a large sample study estimated that 50% of the infected population were infected with variant A, 25% with variant B, and 25% with variant C. A public health researcher randomly selects 100 infected persons to test the hypothesis that the variant distribution is still the same as 1 year ago. It would be a daunting task to look at all the possible combinations we could get here when we're randomly selecting 100 infected persons and putting them each into one of 3 categories. There are many different combinations possible. Indeed, we're not going to have time to do that in our lifetime. So let's look at how we can handle this from a large sample perspective. Here's our null hypothesis, that pi1 is 0.5, pi2 is 0.25, pi3 is 0.25, and all of those are true at the same time. Given that we have a large sample, we can go ahead and set alpha at the common value of 0.05. We have an n of 100. Let's suppose that we obtain these observations: 42 with variant A, 37 with variant B, and 21 with variant C. It's easy enough to calculate the goodness of fit statistic because for that we only need observed minus expected, and expected is based upon these proportions. You might want to try doing it and check my answer here. The goodness of fit statistic is 7.68. Given that we don't have the multinomial distribution, what should we do? Well, one thing we could do is this. Recognize that the goodness of fit statistic under a null hypothesis will asymptotically be distributed like a chi-square with k minus 1 degrees of freedom, where k is the number of groups. In this case, we have 3 groups, so we would use 2 degrees of freedom. All we have to do is calculate the percentile rank of our goodness of fit statistic of 7.68. Of course, taking 1 minus the proportion associated with our percentile rank will get us the upper tail of the distribution. That is where we want to calculate our p-value, and the p-value here is 0.021. You can obtain this with any statistical software. I used R, and the function in R for calculating the probability of a chi-square. I can reject the null hypothesis and conclude with 95% confidence that the variant distribution is indeed different than it was 1 year ago. What is that distribution? I do not know that for sure. I can make my best guess using maximum likelihood estimates, and doing so, I have my estimate of pi1 as 0.42, which would say that 42% of the population that's infected were infected with variant A, 0.37 were infected with variant B, and 0.21 or 21% were infected with variant C. What I have just done is used my goodness of fit statistic with an asymptotic distribution. That is, asymptotically, it will approach a chi-square with k minus 1 degrees of freedom. But there are actually 2 large sample possibilities for calculating the p-value. The asymptotic one is to take the goodness of fit statistic and look at a chi-square distribution with k minus 1 degrees of freedom. That's what we just did. But there's another possibility, and if you've been watching all the videos in all of this non-parametric series, you should know that we can use Monte Carlo methods to obtain an approximate sampling distribution. The multinomial exact distribution can be approximated by randomly sampling many possible observations and using the multinomial coefficient to calculate the probability of these observations when the null hypothesis is true. As long as we sample a large enough number of possible combinations, we can get values that are very nearly exact values for this distribution.